All right, let's have a look at interference. Interference is when two or more waves overlap and form a new amplitude or pattern. Uh, we'll talk first about the principle of superposition, which basically says that the resultant amplitude is the sum of the wave's amplitude at the points at which they're overlapping. So where the waves are overlapping, the superposition says that the resultant amplitude will be the sum of their amplitudes. And so destructive interference is when the amplitude decreases, crest overlapping with the trough, or vice versa. Constructive interference is when it's a crest and a crest, or a trough and a trough, and basically if you have two positive amplitudes, you will get a more positive amplitude. Two negatives will result in a more negative amplitude. An interference pattern, though, is what we're going to look at. It's the pattern formed as a result of two sources overlapping. We'll assume that they're in-phase sources and that they're point sources. And the pattern formed will be a result of constructive and destructive interference sort of alternating as the waves pass through each other. And we have a little demonstration of this here. Right along this middle part here, we have constructive interference, and then we also have constructive interference out here and out here. Same thing here and here, and then along these out this way. So that's all constructive interference. Destructive interference will be along these lines, all in there, like that. So constructive interference I've drawn with the black lines, destructive interference with the red lines. This animation was one I took from Wikipedia, and he said it was open source or Creative Commons, so we can use it for this. So the lines that radiate from the midpoint of the two sources are called nodal and antinodal lines. Nodal lines are the minima. That's where the destructive interference was happening. So node, destructive, minima. Those are all words that go together. The antinodal lines are maxima, the plural of maximum. And those are where constructive interference is happening. And so if we look again at the animation here, there is constructive interference happening all along that antinodal line, again right down the middle. So that's an antinode or a maximum, whatever we want to call it. If anybody asks, that's where n equals 0. Then there's constructive interference again along here. That's where n equals 1 on both sides. So that is the first maximum, central maximum in the middle, first order maximum on each side, second order maximum again beyond that. And then same thing, of course, down here. So those are the maxima. Where we have constructive interference. Destructive interference along here, n is then 0.5, and would be 1.5 for this second order minimum. Third order minimum, n is 2.5. Hopefully you're seeing a pattern emerge here. The antinodal line along the center is the central maximum. As I said, that's where n equals 0. And we say that every point on that line is the same distance from each source. So if we were to do a quick kind of sketch here, if those are the two sources, and then we looked at a point on the line, maybe right here, we see that it's the same distance from each of those. And every point on that line would be, again, the same distance from each of the sources. The next antinodal line on each side is the first order maximum, and there that's a one wavelength phase shift, as we call it, and we'll talk more about phase shifts, but in that case the path difference is 1 times the wavelength. So if we go back to our little drawing up here where we have, and we'll draw a little bigger, our two sources, if we're talking about the a spot on the first antinodal line here, Let's say this is a certain distance here, there's a certain distance there. The distance from the further one would be maybe one wavelength more, or would be exactly one wavelength more. So if this was a distance that we'll call d whatever, then this would be d plus the wavelength. So the path difference will be a whole wavelength. So one more wavelength from the further one than from the closer one. Maxima will occur where the path difference is n lambda, again where n is just some whole number, but where the path difference is not a whole number times the wavelength, there we have destructive interference. And minima is where it's completely destructive interference. And those of you that are thinking ahead, that would be where we have 0.5 less than a whole number times the wavelength. So that's where we have 1.5 wavelengths as the path difference, for example, at the second nodal line. This we can see with any type of waves. The ones we were looking at sort of look like water waves or something like that. We can also get this with light waves. If we take, for example, a laser and pass the laser light through diffraction grating, we'll get bright parts where it's an antinode and dark parts where it's a node. So the bright lines would be the maxima there. With sound, we'd see a similar thing where we'd have it loud along the antinodal lines and quiet along the nodal lines. Now, speaking of sound, we'll take a quick look at beats, or when I say look, I probably mean listen. Beats are basically a different kind of interference where we have, instead of in-phase sources, we have out-of-phase sources where they have or not out of phase necessarily, but sources with two different frequencies. So, for example, if we have a tuning fork at 440 hertz and another tuning fork at 445 hertz, if we play those at the same time, then we'll get a beat frequency. And that beat frequency will be, in this case, 5 hertz. Since that's the absolute value of the difference between them. We can use this for tuning instruments. If we have a reference pitch from a tuning fork or another instrument that we know to be in tune, and we play our own instrument when we're hearing beats, the more beats we're hearing, the greater the frequency difference, and so then we move the tuning peg or we adjust the length of the instrument or whatever we're doing to change the pitch. We can use that to adjust it until we don't hear the beat frequency anymore, and when there's no beat frequency, then they're producing the same frequency and they are in tune. And that's all we need to know about interference and beats at this point.